Hi everyone, hello and welcome. You are watching the series Mathematical Methods for Economics, and this is the 26th lecture in the series. The topic for today's video is implicit differentiation. Implicit differentiation is essentially an application of the chain rule that we covered in the previous video. In this video in particular, we will talk about what implicit differentiation is, when we should use it, what this technique is all about, and how we should apply it. Note that even though we are introducing a new technique here, our objective in the larger scheme of things still is to be able to take a derivative. We're still in the realm of differentiation, and our objective is to find dy by dx, but in a framework which is different from what we've discussed in earlier videos, and that is something we'll talk about. So, while listening to this lecture, don't lose sight of the objective, which is that we have to ultimately find the derivative. The bottom line is that implicit differentiation is a very important tool, and for anyone training to be an economist, this is one technique you must master. The main features of today's talk will be as follows. We will be introducing the method of implicit differentiation, while also bringing in the concept of explicit and implicit functions. We will talk about what we mean by explicitly defined functions and functions that are implicitly defined. The main focus, however, will be on the first order and the second order derivatives of functions defined implicitly. So, the main focus would still be that. And then we later, if time permits, we will also see how we can use the method of implicit differentiation, how we can calculate derivatives implicitly with the help of what are known as total differentials. So, this is the plan of action for today, and we'll carve our way through all of these ideas, these points listed here, with the help of some worked out examples. These are examples which I've borrowed or adapted from several textbooks, and these are quite illustrative. So, let's begin. We will first talk about a function that is defined explicitly. So, if we go by the story of whatever we've discussed in the topic of differentiation so far, we have so far talked about how to differentiate functions. Functions which are defined, which are described by an equation such as y equal to f of x. Now, here this is an equation where we say that y is defined explicitly as a function of x. We can ask here, what do we mean by a function that is defined explicitly as a function of x? So, there are two things to note here. In this equation, the structure of this equation is such that the variable y appears all by itself. So, if you notice the structure of this equation, y equal to f of x here, the variable y appears all by itself on one side of the equation. So, basically you are able to separate out the x and the y variables and the constant and separate them out in such a way that y appears all by itself on one side of the equation. And you can see some examples that I've put here on this slide. So, for example, if let's say y is equal to x squared minus 4x plus 5, y equal to natural log of e to the power x minus 1 minus x, or even y equal to the cube root of x. There can be infinitely many examples that we can put here. But the point here is that all of these equations, they define a function in explicit form where y appears all by itself on one side. But note here that it's not just enough to just have y appearing, the variable y appearing all by itself on one side of the equation. Remember that this other aspect is also very important, that equally important, that you should also have a functional relationship. So, for instance, I might give you an equation which is of this kind, y equal to plus minus square root of x. So here you can clearly see that I have separated out the y and the x variables, and y is entirely by itself on one side of the equation, but then this does not define a function. So don't lose sight of the fact that there has to be a functional relationship. So whichever way you're writing it, there has to be a functional relationship. And in this case, when we define a function, when we describe a function by the equation y equal to f of x, that is basically a function which is defined explicitly. Now let us suppose we have functions, we are differentiating functions of the form where the function is implicit in equations such as, I have given you 3 examples here, x times y equal to 5, or x squared plus y squared equal to 9, or even an equation like this such as x plus y cubed equal to y to the power 5 minus x squared plus 2y. So basically here the function we are saying is implicit in these equations. Now let's just pause for a moment and understand what we mean by implicit. See, if we look at the English meaning of implicit, the word implicit means not expressed in a direct way. And that is exactly what is happening here. There is a functional relationship. So if we were to talk in Hindi we would say that functional relationship जो function की information है वो सीधी तरह से नहीं दी हुई इन equations में. And you may or may not be able to unravel the information that is embedded about the function in these equations. That is a different matter. But the point here is that there is some information about a function, or even it could be more than one function, that is embedded in each one of these equations. And I have chosen these equations in such a way that each one tells a story, and these cases will be exhaustive. So there is some information which is embedded about the function in each one of these equations. It could be information about one function or several functions, but there is information embedded. It's not expressed in a direct way. It is not expressed in a direct manner, but that information is there, and whether or not you're able to unravel that information, so whether or not you can write the function in explicit form, that is another matter. Now, what is the main message of today's lecture? The main message is what comes through this method of implicit differentiation. What the method of implicit differentiation tells us is that it does not matter whether or not we can unravel the information about the function or functions in these kinds of equations. So do you see that we have changed track? We have moved from functions that were explicitly defined, as in the previous slide, to equations now where the functional relationship is embedded in these equations. So the point is the method of implicit differentiation is saying, what it is saying is that it does not matter whether or not we can unravel that information. We can still use the method of implicit differentiation to calculate our dy by dx, to calculate the derivative of a function at a given point, which is to say that if we want to find the slope of the tangent to the curve at a given point, the tangent to the graph at a given point of a graph specified by any one of these equations, that is something we can easily achieve through implicit differentiation. So what we'll do now is that I will walk you through each one of these equations one by one, because each equation here tells a story, and let's see what exactly we're trying to convey here. So let's look at the first equation, which is x times y equal to 5. Now here you can clearly see that this equation is not of the form y equal to f of x. Y is not explicitly defined as a function of x, because y does not appear all by itself on one side of the equation. However, this is a very simple case. In this case, we can always rewrite the equation so that y appears on the left here, and we can rewrite this equation as y equal to 5 by x, which is then the explicit form. So this is the case where you can separate out the y in such a way that you can write y explicitly as a function of x. So the equation as such, xy equal to 5, the equation as such defines y implicitly as a function of x. Implicitly is simply saying that the information is there, we just haven't expressed it in explicit form, right. So, the equation x times y equal to 5 defines y implicitly as a function of x, and in this particular case we can also write the variable y, the function, in explicit form. In fact, we can even grab a visual of this particular graph. So, x times y equal to 5, we have the graph of this equation here, and this will lie in the first and the third quadrants, as you can see. So, let us suppose, because that is the ultimate objective for this particular video, that we should be able to find dy by dx, the derivative, which is nothing but the slope of the tangent to the graph at any arbitrary point, let us say A. So, let us suppose we have this point A, and we want to find the slope of the tangent to the graph at A. So, one way you could easily do it is, and because this is a simple example, you could easily write y as 5 by x, y is equal to 5 by x, and then take the derivative, which is dy by dx equal to minus 5 by x squared, using the power rule. But what the method of implicit differentiation is saying is that we do not need to, and sometimes we may not even be able to write a function in explicit form, and in that case we can use the method of implicit differentiation. So, let us see how this method of implicit differentiation works and how it helps us arrive at the expression for dy by dx. Now, in this equation, x times y equal to 5, since the equation defines y implicitly as a function of x, we have already seen the functional relationship embedded in this equation, we can write, because y is implicitly defined as a function of x. So, instead of y, I can replace y by f of x and write the equation as x times f of x equal to 5. So, our equation now is rewritten as x times f of x equal to 5. Okay, so in this case we have that the derivative of the left hand side must be equal to the derivative of the right hand side. So, because the derivative of the left hand side must be equal to the derivative of the right hand side, we can differentiate both sides of this equation, x times f of x equal to 5 with respect to x, to get the following. So, on the left hand side we will be using the product rule, which then gives us the first variable, the first function, x times the derivative of f with respect to x, f prime of x, plus f of x, a second function, times the derivative of x, which is 1, and because the derivative on the right hand side we have a constant, so the derivative here on the right hand side would be 0. Okay. Now we have this particular expression, and we can solve this equation for f prime of x to get minus f of x divided by x. So, this is nothing but minus y upon x, as you can see. In fact, suppose, so our point of interest was we wanted to be able to calculate the derivative at this point such as a. If you look at the coordinates here, x is equal to 2. So, you can see that dy by dx we calculated as minus 5 by x squared. So, x here would, because x is 2, x squared would be 4. So, dy by dx at this point a would then be equal to minus 5 by 4, which is minus 1.25. Now, in the explicit form we got dy by dx as minus 5 by x squared. The question is it the same result that we are getting here? Because ultimately both the approaches should give us the same result, and the answer indeed is yes, because this is nothing but minus y by x, and as you can see here y is nothing but 5 by x. So, once you substitute for y, you are going to get minus 5 by x squared, right. So, that is how we calculate f prime of x. Now we can also go a little easier on notation, and this is actually the more common way of differentiating, performing implicit differentiation. So we can actually differentiate directly and not use this notation f of x. So if we differentiate directly while assuming that y defines y is implicitly defined as a function of x by this equation. So we can differentiate both sides of this equation, x times y equal to 5 with respect to x, to get again we are going to be using the product rule. So on the left hand side we have x times the derivative of y with respect to x, so dy by dx, plus the second function, which is y times the derivative of x, which is 1, so plus y times 1 is equal to 0. And this you can then solve for dy by dx, which is nothing but minus y by x. And this is exactly what I was talking about earlier, that if I substitute, so I can leave the answer like this, my result as minus y by x, or because this is the case that we are doing right now is one where I have the explicit form for y, so I can always substitute for y, and you can see here that because y is equal to 5 by x, that then gives me dy by dx explicitly defined in terms of x, which is then minus 5 by x squared. And just as we calculated the derivative at x equal to 2, we can do the same thing here to get the same answer, which is minus 1.25. So this is as far as our first case goes. Now let's look at this particular case, this second example here, which is also quite illustrative. Now here our equation is x squared plus y squared equal to 9. And as all of you know, that this is the equation of a circle with the radius 3, and it's the circle which is centered around the origin. So that is what we have here. And again, let us go back to our main question. Suppose I want to calculate the slope of the tangent to this curve at a point like A. Okay, I want to find dy by dx at this point A. Now here there is an issue, because you would think that well, this is a circle, we don't have a function here. So if we don't have a function, how do we take dy by dx? And there is a simple answer to this. There is a simple way of going around this problem, which is that even though the circle does not pass the vertical line test, which is to say that there will be in this case two values for y for every x in the domain, but we can always break this graph up, break up the circle into two parts. And here we can divide it into two parts. One is the upper semicircle, which then represents the graph of the function y equal to plus square root of under root 9 minus x squared. And the second part is the lower semicircle, which is representative of the function y equal to minus under root 9 minus x squared. So even though the circle as such, x squared plus y squared equal to 9, the equation as such does not give us a function, we can always describe it in terms of two differentiable functions here, and then we can use either one of these. So wherever our point lies, because in our example A was here in the second panel, where with the lower semicircle, that portion of the graph. So we can always use any one of these two explicit forms to calculate a dy by dx. Now that would have been the way you would have done things in the earlier days, but this is where the method of implicit differentiation again comes in and says that you don't need to define y explicitly as a function of x. You can just go ahead and differentiate both sides of the equation to get your dy by dx through the method of implicit differentiation. So let's see how that works for the circle here. Our equation is x squared plus y squared equal to 9. Okay. Now, if we again, because the derivative of the left hand side will be equal to the derivative of the right hand side, and that's the way the process of implicit differentiation works, that we differentiate both sides with respect to x, assuming that y defines y is defined implicitly as a function of x, and here when we differentiate both sides with respect to x, we get, and here you can see it's the derivative of x squared plus y squared with respect to x on the left hand side. Now, because the derivative of a sum is a sum of the derivatives, so on the left hand side we will have 2 times x, right, plus, now if you look here, if I have to take the derivative of y squared with respect to x, how do I do that? Now, many of you would already know this, that it's 2y times dy by dx, but what exactly are we doing here? We are actually using the chain rule here, right? So, that is why I said in the beginning of the lecture that this method of implicit differentiation is nothing but an application of the chain rule. So, when we have to differentiate y squared with respect to x, so we can, if you really want to get into the detail, you can, let's say, put z equal to y squared, and then dz by dx would be equal to, by the chain rule, dz by dy times dy by dx. Now, dz by dy would be 2 times y, because z is equal to y squared. So, dz by dy is 2 times y, and that is then multiplied by dy by dx. Okay. So, we have here then that the derivative of y squared with respect to x would be 2 times y times dy by dx, and on the right hand side we will again have 0. Solving this equation then with for dy by dx, we are going to get dy by dx, we can take 2x to the right hand side, you are going to get minus 2x divided by 2y, the 2's will get cancelled, and you will get minus x divided by y as your answer. So, this is how we are going to carry out the process of implicit differentiation to find dy by dx for x squared plus y squared equal to 9. Okay. This is the last example that I wanted to show you in those 3 equations that we had on the earlier slide to discuss implicitly defined functions. Now, if you look at this equation here, x plus y cubed equal to y to the 5 minus x squared plus 2y. This is no easy equation, and it doesn't look like it's possible to solve the equation explicitly for y. If you are able to do that, if you are able to separate out the x and the y variables such that y appears all by itself on one side of the equation, please put in the details in the comment box, but it doesn't look like it's possible here to solve this equation explicitly for y. But it is still possible to find an explicit expression for y prime, which is nothing but dy by dx. So, let us see how we can do that, and for this let us suppose that the equation that we have here, x plus y cubed equal to y to the 5 minus x squared plus 2y, let us suppose this equation defines y as a differentiable function of x in the neighborhood of this point 1 comma 1. As you can see, this point satisfies this equation. So, on the left, if I put 1 comma 1, I am going to get 2, and on the right, if I put 1 comma 1, x equal to 1 and y equal to 1, I am going to get 1 minus 1 plus 2. So, both sides we have a 2, it satisfies this point, certainly satisfies this equation. And let us suppose that y is defined as a function of x, and this is implicitly defined as a function of x and satisfies this equation, x plus y cubed equal to y to the 5 minus x squared plus 2y. So, the question here is find dy by dx at this point 1 comma 1. Again, we will differentiate both sides with respect to x. Once we do that, we are going to get on the left hand side 1 plus, again we are going to be using the chain rule. So, we are going to get 3y squared times dy by dx, which I am writing as y prime here. And on the right hand side, I am going to have 5 times y to the power 4 times dy by dx minus 2x, because the derivative of x squared with respect to x would simply be 2x and with a negative in front, because there's a negative in front of x squared, plus 2 times dy by dx. So this is what we get when we differentiate the equation, both sides of the equation with respect to x. Now we can collect all the terms that contain y prime, and we can do that in order to get our dy by dx. So once we collect all the terms that contain y prime, I have, you can see here, 5y to the power 4 plus 2 on the right hand side. So those terms I already have here, and then I bring the 3y squared on the left to the right hand side. So that becomes a minus 3y squared. The whole thing times y prime is equal to 1 plus 2x, and this I can then solve for y prime, which then gives me y prime as 1 plus 2x divided by 5y to the power 4 minus 3y squared plus 2. And because our objective was to find dy by dx at the point 1 comma 1, we can just plug in these values here. So that will give me 1 plus 2 in the numerator, which is a 3, and in the denominator I'll have 5 minus 3, which is 2, plus 2, 4. So y prime or dy by dx at 1 comma 1 is equal to 3 by 4. So with this we conclude the first part of our discussion on implicit differentiation. Thank you.